Hey everybody, welcome back to the channel. It's been a while. This one has been on the back of my mind to put out for some time. It's been a while since I put a video. I've been pretty busy, but I got a little bit of time here. I can go through this updated way of calculating voltage drop. So if you're aware of this, that's great, but many people are not aware that there is an actual change to how we calculate voltage drop and a change to the D3 tables of the Canadian Electrical Code. I do have a video. I'll try and get that link in the comments based on how it used to be done. It's still good to review that because in that video I go through 8102, which talks about voltage drop. I'm not going to do that in this video. This video I'm just going to show you how to calculate voltage drop and a few other calculations based on the new methods in D3. Okay, so let's get into this. Let's make this short and sweet. The reason I say that is some people comment that the videos are too long. And my logic to that is, well, then don't watch the entire video. Just skip to what you want. But yeah, sometimes they do get a little bit long. So I'll try not to make this as long, but it's still going to be somewhat in depth. So feel free to skip ahead. Okay, so let's just go right to D3. And again, this all comes from 8102. So one of the first things you're going to notice is now they have this chart called K values. So K values for calculating voltage drop in an installation of 2, 3, or 4 insulated conductors in a cable or raceway based on a conductor operating at 75 degrees. Well, that one's interesting because most of the time your conductors are based off 75 degrees when you're connecting to equipment that is only rated for 75 degrees. Now there is caveats to that. Once you're 1.2 meters away from that equipment, I believe it's 1.2 meters, then you can use the full 90-degree rating. But I typically just, I always use 75 degrees unless it's a bigger wire and I'm going to save some money. Okay, so yeah, you got this table D3, K values, which is more or less just resistivity, a measurement of ohms, resistance of a given size conductor of a size per foot. Right? So along the left side of the column here, or the table, you got your wire gauges. So starting at number 14 all the way to 1000 MCM. Along the top you got your conductor material. So is it copper or is it aluminum that you're working with? The old tables did not have this. All right, so now they dictate copper and aluminum. I think there was a note in the old tables with respect to aluminum, but here it is actually shown. Now what they also show you is, in this new chart, is it going to be a cable or raceway, right? And really where this comes in, so you got cable or raceway, you got cable, raceway for copper, same thing for aluminum. But when you look at the next row below it, you got DC values, right? So if you're working with DC. But then to the right of that, you have power factor. So that's been added in, right? So now we need to know the power factor of the circuit, right? So if you have 100% power factor, and it's copper, it doesn't matter if it's cable or raceway installation. These are your values based on the wire gauge. Now if it's a cable installation, 80% or 90% power factor. Okay, and there's your values, respective values. If you're in a raceway, whether it's PVC, EMT, rigid steel, rigid aluminum, it's a raceway, right? Here's your values for those based on the power factors. And the same thing applies to aluminum conductors. Okay. Always make note, Appendix B, we're not going to go there, but you should go see what that says. Also make note of the little cross here. That means there's a note down below. Sorry for this being a little blurry. It's just how it's scaled in when I brought it in for my screenshot. But you got your code book, you can check this out. Okay. The next page I would follow, and I'm going to get there, but it actually starts at the bottom of D3 because it shows you a bunch of formulas. Okay, and it's nice because it tells you there's a whole bunch of formulas here, but it's pretty straightforward what they're for. They tell you what they're for and when to use them. So for example, number 1 here, voltage drop for known conductor size. So you're going to use, say, number 14. So you can calculate the voltage drop of a known conductor size from the table using the following formula. So voltage drop would equal, and again, sorry that is really blurry, but it's K times F times I times L divided by 1000. And to break that down, K is the K value coming from up here. These K values. Okay, that's what the K is for. And it explains it better on this slide coming up next, or on the next screenshot. F is the voltage drop factor. We'll get into that. I is for the current on the circuit. L is for the length of the circuit in meters, and divided by 1,000. Okay. And here's a better shot here of what everything means. Okay. When the conductor size is not known, so you don't even know what size you need, right? The maximum K factor can be calculated using the formula. So you would calculate the K factor, which then would tell you the minimum size conductor required. And to use that formula, you got to know how much voltage will be dropped on that circuit, times it by 1,000, divided by the current that will be drawn on that circuit, the length of the circuit, and the voltage drop factor. Okay, and we'll talk about what this is in a second. When the conductor size is known, you can find out what the maximum length of that conductor installation can be. So the length has to be less than or equal to, that's what this means here, right? Less than or equal to permitted voltage drop, or how much voltage drop will be dropped on the circuit, times 1,000 divided by the current, times the K factor, times the voltage drop factor. And then last one, how much voltage drop as a percentage. You can calculate that basically by the actual voltage being dropped, right? Not the percent being dropped, but the actual voltage divided by the circuit voltage times 100. That will give you the percentage. Okay, and I got an example coming up to show that. All right, so I'm not going to go through these. These are self-explanatory. You can read those. But I do want to look at the F, the form factor, or the voltage drop factor. Right? So this is new as well in the new code book. And maybe it would be easier. I don't know. Let's see here. If I bring over my code book, maybe it'd be clearer for you if I do that for you. I'll just zoom in. Yeah, I think this is a lot cleaner for you. How's that? Okay, so the voltage drop factor, F, can be determined from the following table. Okay, so the type of electrical system, is it a DC circuit? Is it single phase or three phase? Next row or column, the type of circuit for electrical load, right? The number of conductors. I don't really do, well, I shouldn't say I don't do a lot of DC because I do a lot of controls design, but I don't do anything that involves a lot of distance I'm worried about. All my designs are within the control panel itself. But if you were, right, do you have a 2-wire, which is positive to negative, positive to grounded conductor, and so on? Do you have a 3-wire line to line with grounded conductor, right? The next column over would be the F factor. Notice how basically it's all 2, except for when you get into 3-phase. So everything is going to be form factor of 2, except for if you have a 3-wire, which is line to line with no grounded conductor, so like a delta system, just line 1, 2, 3, or a 4-wire. So you got your 3 phases and a neutral, your grounded conductor, right? Those are the only 2 times you can have 1.73. Other than that, your F value is always going to be 2, according to this chart. Okay, so that is that. That is the big change compared to the previous code book. Again, look at my older videos if you want to reference what it used to look like. But yeah, big changes. And I've worked this out with some previous voltage drop calculations, and you basically get the same answer. This just gives you, I think, more formulas and better options. I don't know, honestly. I've gotten used to using this as opposed to the old method. So I'm just going to run with it and stick with it. But let's go to our questions that we're going to do for this video. Okay, so we're going to do 3 questions, and I got these pre-worked out. Should be pretty good. So if you hear me fumbling paper around, that's because I already got pre-worked out just to speed this video up and make sure my numbers are correct. All right. So question 1, what's the maximum distance that a number 14 NMD90 copper wire can be installed for 120 volt, 8.5 amp load? The circuit cannot have more than a 2% voltage drop. And for anyone reading this, what is the maximum voltage drop that you could have by code, honestly? Think of that in the back of your head, because that's going to be coming up later on. Okay. The hint is 8102. It's in there. The circuit will have a power factor of 80%. So there's a few added things in here that I had put in to be able to do the new formulas. Now I'm telling you the power factor. All right. I'm telling you that's actually a cable, a copper wire, NMD90. It's a cable. Right. I have to tell you whether it's in the cable or a raceway. Right. And this one I'm saying for this circuit, you can't have more than a 2% voltage drop. Okay. So knowing this, what formula could we use? All right. So maximum distance on number 14. What is the maximum distance that you can use? If I go back to the formula page, let's see. When the conductor size is not known, so we're not going to use that. When the conductor size is known, the maximum cable length can be calculated using the following formula. Length is less than or equal to the voltage drop times 1,000 divided by the current times the K value times the voltage drop factor. Okay, so let's do this slow. Let's get this down. Center that up. And then, yeah, let's do this. So I'm going to do a red pen here. So we've determined that we're going to look for the length. And our length has to be less than or equal to, right? Voltage drop times 1,000 divided by the current times K times voltage drop factor. Okay, now we know most of the stuff here already. We know the current, all right? So we know the current. The K value is going to come from D3. All right, so D3. And the voltage drop factor is below it. Okay. What we don't know is this. How much voltage is going to be dropped on this circuit? Okay, so for those who have been thinking about what is the maximum voltage drop that you're allowed on a circuit, it's 3% for a branch circuit. But here I'm telling you that you have a maximum of 2% voltage drop. So we need to find what the voltage value is for VD. Okay, we know it's a 120 volt circuit. So basically, we can find VD by taking 2% of the 120 volts. This is my circuit voltage. This is my allowable voltage drop. All right, so basically 120 times 0.02 equals 2.4 volts. That's going to be our VD. Okay, that's the maximum voltage that we're allowed to drop on this circuit. We're only allowed to lose 2.4 volts. Okay, but now that we have this, we can do the rest of the circuit. Let me change up the color for you here. Okay, or we can do the rest of the formula. So now we just fill in the blanks. So 2.4 times 1,000 divided by the current. Our current's 8.5 amps times the K value. Okay, so we need to find a conductor, I guess, to handle the 8.5 amps. Well, actually, no. I'm telling you that. It's number 14. So we know it's number 14. I'm going to drag my code book back over because it's a lot clearer. We know it's a cable. And I said the power factor is 80%. So at number 14, it's a cable, 80%, 9.67. That's our K value that we're going to use. Okay, so just enter 9.67. 9.67 times our voltage drop factor. Okay, so if I go back to here, and I'm just going to keep dragging this back because it's a lot clearer. That's this chart here. Right? We have a 14.2 NMD90 Right? I know it's a 2 conductor because it's just 120 volt circuit. Let's just assume a 14 too. So it's basically a single phase AC, 2 wire, line to grounded conductor, 2. And again, remember I said it's basically going to be 2 no matter what until you get to these 2 last scenarios here, which is 3-phase AC installations. Okay. But for this question, it's 2. So just enter 2. All right, move this around. So now that we know that, we can solve. So less than equal to, we're going to get, we're going to end up with 14.6 meters. If you calculate this out, you get 14.6 meters. So that is the maximum length that we can go with this 8.5 amp load with no more of a 2% voltage drop and a power factor of 80%. Okay, so again, first step we have to do, because this formula needs to know what voltage, not percent, but what voltage will be dropped. And I'm saying 2% voltage drop max. So that's how we get the 2.4. I just found 2% of 120 volts. That was the circuit voltage. Right? And then we knew the current. The K factor came from D3, okay, which was, we're using a number 14. We have an 80% power factor, and it's in a cable, so 9.67. Okay? And then our form factor, or I keep saying form factor, our voltage drop factor is 2. Do the math, 14.6 meters max. Okay? So that answers question 1. Not too bad. It's not too bad because I give you the formula what to use. Let's look at the next one here. Okay, question 2. What would be the voltage drop of a 347 volt, 3-phase, 3-wire installation drawing 24 amps on a number 10 copper conductor in a PVC raceway, and is this installation code compliant according to 8102? The installation is 15 meters from the overcurrent device to the load. The circuit has a power factor of 90%. So the question is, what would be the voltage drop? All right, so let's go look at our formulas that we had and see what we can use. Voltage drop for a known conductor size. I think this one right here, right at the bat, because we know the conductor size and we want to find voltage drop. So voltage drop will equal the K value times the voltage drop factor times the current times the length of the circuit divided by 1,000. Okay. All right, let's do another fancy color here for you. So voltage drop equals K times F times the current times the length over 1,000. Okay. So our first step, I guess, we just fill these in. So what's K? Well, let's go find out what K was. Let's keep in mind that we are using a number 10 conductor, and it's in a raceway with a power factor of 90%. Okay, so if I go down to my D3, a number 10, it's in a raceway, and I said it has a power factor of 90%. So we're going to have a K value of 3.96. Okay, in a raceway. And we're using copper. I think I mentioned copper. I did mention copper, so good. All right, so our K value is 3.96. Now our voltage drop factor. What kind of circuit do we have? We have a circuit that's 347 volt, 3-phase, 3-wire. Okay, so again, let's go to the other table. It's a 3-phase AC system. It's a 3-wire. So there is no grounded conductor. It's not a 4-wire. So we are doing 3-wire, line to line. Right? So 1.73. Okay, that is our F value. 1.73. Okay. Times the current. We're saying it's going to be 24 amp load. that's drawing on this circuit, and the length of it in meters is 15. Okay, so just highlight that. 15's come from here. Here's the circuit characteristics. So number 10. Okay, and we said it was a power factor of 90%. Okay, so that's where we got all these values from. You calculate all that, divided by 1,000. I'm just going to round up. So basically you get 2466 divided by 1,000. And our voltage drop, the amount of voltage we will drop on this circuit is 2.5 volts. So again, is this code compliant? Well, it is. Right? There's no way we're drawing more than 3%, right, of the voltage. And let's just do this. Let's just work this out. So 347 times 0.03. We're allowed to drop 10.41 volts on this circuit. We're only dropping 2.5 volts. All right, so we are good. It's code compliant. We're good to go. That's how much we're going to drop, how much voltage. Okay. All right, question 3. This will be the last one here. So this one, you don't know the conductor. You got to figure, okay, I got this installation. I know I'm using T90 conductors, copper. I'm terminating the 75-degree equipment. It's a 240 volt 3-wire circuit, so 2 lines in neutral. Resistive heating, so because it's purely resistive, it's going to be 100% power factor. It's a 40 amp load and it's 23 meters from my overcurrent device to the load. What size conductor can I use for this? All right. So again, let's go back and look at the options we have for formulas. All right. So if we go here, well, we can't use this when the conductor is known. The one above it, though, when the conductor size is not known. So we need to calculate the K value. The K value cannot be more than, has to be less than, or equal to this calculation. Okay, so that's what I kind of like about the updated. It gives you some formulas you can work with and tells you when to use them. So I like that. All right, let's see. Let's do what color we want today. Let's see how, I guess let's use orange. Let's see how that shows up. Not that it really matters what I use, but. So we're going to calculate the K value, and it has to be less than or equal to voltage drop times 1,000 divided by the current times the length of the circuit times the voltage drop factor. Okay, so again, we got this VD. We got to find the voltage drop, the amount of voltage that would be dropped in this circuit. Okay. Now, we're allowed a 3% maximum voltage drop in a branch circuit. I'm not specifying maximum voltage drop as 1%, 2%, like I did do a 2% in a previous question. I think question 1, we did that. Here, if you're not told the maximum voltage drop on the circuit, you're allowed 3%, according to 8102. Okay, so the voltage is 240 volt. 240 volt. So let's find 3% of that. So 240 times 0.03 equals 7.2 volts. This will be VD. Okay, that's the maximum amount of voltage that we're allowed to drop on this 240 volt circuit. Okay, so now we can solve. Let's go back to here. Okay, so 7.2 times 1,000 divided by the current, it says 40 amps. The length is 23 meters. And now we got to find our F value. It's a 240 volt 3-wire circuit. It's a single phase, line 1, line 2 with a neutral. So just to show you, right? 2-wire, or 3-wire, sorry, 3-wire line to line with grounded conductor. All right, 2. Everything's going to be 2 except those last 2 installation scenarios. So 2. Okay. Do the math. I'm just going to round up in this, 7200 divided by 1840. Let's move this up. Equals 3.91. All right, well, cool, 3.91. That's what the K value equals. And actually, let me back that up. What we're saying is our K value has to be less than or equal to 3.91. So we cannot exceed this, okay? Do not exceed. That's a sloppy. Do not exceed. Okay, so what do we do with this? Let's go look at D3 and find a value that is equal to or less than 3.91. And this is going to tell us our minimum conductor size. So 3.91, we're using copper. Oh, and what else did I say? Did I say it is T90 conductors? So obviously it's going to be an raceway. Where's my code book? So it's in a raceway, 100% power factor. So honestly, it doesn't matter. It doesn't matter. Copper, cable or a raceway with 100% power factor, you're coming down here. So we had 3.91. We need a number that's equal to or less than. So if we go down this column, or this column, well, we can't use the number 10 because that exceeds 3.91. So a number 8, right? We can use a number 8 conductor. So get back to here. So therefore, a number 8, which is equal to 2.54. Okay, so remember, you cannot exceed. It has to be less than or equal to 3.91. If you want to use an even bigger wire, that's up to you. But this is minimum, right? That's your minimum size. You want to use a number 6, knock yourself out, right? But this is minimum. Okay, so I hope this video kind of clarifies the changes to the new way of calculating voltage drop. If you got any questions, comments, let me know. Even if you see maybe a mistake I made, I don't know. Like, I just learned this myself. I figured it out. But I do feel it's correct. Love to hear your comments, including what else you'd like to see. All right, thanks for watching.